Hello! It is my pleasure to introduce the senior project for ZuiDesigns, the hardware-in-the-loop modular test proof of concept. The team consists of Andres Mora, Ryan Vanoss, Ryan Hilbert, Ben Berger, and McKenna Dillevin. The team is sponsored by ZuiDesigns with 3 faculty advisors, Professors Brockera, Zuidema, and Dunn. Hardware-in-the-loop testing is the process of simulating real-world events using electrical signals. These signals are given to a device under test in order to make sure that its software is working as intended. Hardware-in-the-loop testing is often used to test embedded systems. Embedded systems are self-contained electrical devices critical to a wide range of industries, including transportation, biomedical, instrumentation, among many others. In today's industry, hardware-in-the-loop testing is done mainly on a case-by-case basis. Our tester is custom-made to provide a low-cost alternative to existing hardware-in-the-loop technologies, which can be used for a variety of applications in many different industries. But how does a product become usable to so many different industries? In this video, we will go over the design on a technical level and show you how this is accomplished. The mechanical design for the hardware-in-the-loop testing device is a modest, box-like enclosure made out of 1/4-inch polycarbonate. Each side of the enclosure will be laser engraved until cut, and then fastened together using plastic corner brackets and screws. In order for the testing device to interact with the device under test, DB9, DB37, banana plugs, and standard Ethernet, USB, and HDMI ports had to be accounted for. The image on the left shows the front view of the hardware-in-the-loop testing device, as well as the cooling fan. The legend on the right corresponds to the associated electrical connections in the image. This image shows the rear view of the enclosure. This side features the power inlet as well as a power switch, making it easy to manually shut down the entire system if necessary. Additionally, the USB and HDMI ports are located on this side, so that any end-user interaction with the testing device doesn't get in the way of the communication between the testing device and the device under test. The image on the left shows the major interior components of the testing device. The mechanical design allowed for 2 different locations where air can enter the enclosure, and 1 where it can exit. These were placed so that hot air can be pulled away from the PCB, with cool air replacing it from 2 different directions. Power is distributed throughout the entire system via a 120 to 15 volt DC converter. From here, voltage dividers are used to step down to whatever voltage is required. The GPIO for the hardware-in-the-loop testing device features 5 different voltage levels: 1.8, 3.3, 5, 12, and 50 VDC, with the 50 volt output sourced from an external power source. In order to have so much I/O, the CY8C9560A GPIO expander chip was used in conjunction with an FT201X USB to I2C converter chip. This chain allows for a Raspberry Pi to communicate to the GPIO over a USB connection. These block diagrams show how these 2 chips connect in order to form this chain. The output circuits themselves required current limiting and an active voltage regulator to help control the output voltage. Using the LM324 op-amp in the voltage follower configuration, this voltage regulation was easily achievable. Changing the resistor sizing allows for different voltages to be fed to the device under test. This circuit is shown in the image on the bottom right. The upper right image shows how the input channels were designed. These circuits take in a voltage from the device under test and determines its logic level by utilizing the LM2901 op-amp, which is a comparator. Changing the resistor sizes forces the system to look for different voltages when determining the logic level. This logic level is then mapped to a 3.3 volt signal, which can be directly read from a pin on the CY8C9560A expander chip. The image on the left features a transistor network to safely turn 50 volts on and off. This too is controlled by the CY8C9560A expander chip.
The project also contains 2 channels enabled with CAN communication. The CAN chip chosen was the MCP2515, which is a standalone CAN controller with SPI interface. The chip uses CAN v2.0b at 1 megabit per second, and it has a high-speed interface of 10 MHz. In order to interface with this chip, the TJA-1050 high-speed CAN transceiver was used, which is used for high-speed automotive applications. Because the MCP2515 uses an SPI interface, the FT220X chip was used to convert the interface over to USB. This data would then be sent to the USB hub and then to the Raspberry Pi. The PCB for this project was separated into 3 different boards: the inputs, the outputs, and the miscellaneous components, such as the DAC, ADC, and CAN modules. This was to save space within the enclosure. The output board contains all of the output connections from the tester to the device under test, as well as the through holes to house the Raspberry Pi and the ESP8266. The boards all have access to 15 VDC from the AC to DC converter, where the first access point is on the output board. The 15 VDC and the power from the Raspberry Pi are all attached to the PCB using screw terminals. Decoupling capacitors were placed near all of the active components. All 3 boards were 4-layer boards in order to provide easy access to the power and ground. The boards each have differing voltage planes based on the needed voltage for the majority of the ICs. The input board contains a 3.3 internal plane, the output board contains a 15-volt internal plane, and the miscellaneous board contains a 5-volt internal plane. All of the boards have polygon pores connected to ground. The footprints used for the components were found using an online library called SnapEDA. Most of the resistors used had the 1206 packaging, though there were a few resistors that required a larger package in order to handle the desired power through the component. This is the input PCB, and this is the miscellaneous PCB.
The analog signal controller consists of 2 MSP432 microcontrollers, each with 3 peripheral modules. Together, this collection of chips is labeled as the analog signal controller. 2 modules are common between the 2 MSP432s. The first is a 48 MHz oscillating crystal that will drive the clock system. The second is a 15 MB SRAM chip to store waveform data. One microcontroller is connected to a 4-channel ADC chip, and the other is connected to a 4-channel DAC chip. Between the 2 microcontrollers and their peripherals, analog input and output between 0 and 5 volts is achieved. The ADC in use is the Texas Instruments THS1206 chip. Each channel supports 1 megabit per second sampling speed with a 12-bit resolution via the successive approximation method. The DAC in use is the Analog Devices AD7305 chip. Each channel supports 1 megabit per second output speed with an 8-bit resolution. The analog signal controller will remain in an idle state until it is prompted by the main Raspberry Pi that a test is required. It will then send timing information and waveform data for the DAC to the 2 MSP432 controllers. The timing information includes which channels to activate and when to activate them after a start signal is received from the Raspberry Pi during a test. The analog signal controller is programmed according to the state diagram, with an idle state and several logical pathways to achieve functionality.
A Raspberry Pi 4 is the main controller of the hardware-in-the-loop tester. It interfaces with all the other modules. The block diagram shows how the Raspberry Pi interacts with the various signals. These include digital and analog signals, as well as other types of communication protocols, like CAN bus, Ethernet, Wi-Fi, I2C, and SPI. The Raspberry Pi controls the entire testing device. It checks the remote GitLab repository for software updates and new test scripts to run. It stores and runs test scripts, as well as formatting the test results. A new thread is spawned for each test that takes place. The Raspberry Pi programming flowchart shows how the Raspberry Pi controls the testing device.
Now I'll be going over how a user can interact with the hardware-in-the-loop tester. So we've outlined 5 use cases that allow the user to achieve something using the Hill tester. Use case number 1 is running a test file from a remote Git repository. This will allow a user on a remote workstation to push a test file onto a Git repository, which will then be executed on the Hill tester. Use case 2 is running a test file by remotely connect to the device. This will allow a user via network connection to remotely connect to the device and run a test file that exists on the Hill tester. Using the same remote connection, a user can schedule a test file to be run or executed at a future date. So this will allow a user to run a test overnight or sometime next day, etc. Use case number 4 is updating software running on the testing device. So if the user wants to update how the peripherals are programmed in the user library or how some of the scripts work, they will be allowed to do this. User library and scripts will be shown here shortly. Use case 5 is used to access the system log to initiate an email with system log information. So this will allow the user to view the system log or to email themselves the information in the system log. So to implement these features, a user library will be provided. The user library is written in C++ and it will allow the users to control peripherals with easy to use functions. It will allow the creation of test reports and the emailing of those test reports. The user library will be written in such a way that the programmer doesn't need to know specifically how all of the peripherals work. It'll be easy to use so they can focus on programming and testing the device under test. To achieve functionality, some bash scripts will be provided. The view system log script will allow the user to view the system log within a remote connection. The email system log script will allow the user to email themselves the contents of the system log. The initialize script will initialize all of the peripherals connected to the hardware in the loop tester. The schedule test file script will allow a user to schedule the execution of a test file at a future time. The run test file script will allow the compilation and execution of a test file as soon as the command runs.